Questions 37 to 39 in the ACER purple paper. Question 37. Anaerobic respiration is likely to be the only respiratory metabolic mechanism. So in figure 1, we've got a graph with various stages of hatching. So at the end, we've got the bird in the fully hatched stage. Before that, external pipping occurs, and before that, internal pipping occurs, and before that is our the moments before internal pipping. And at each of those stages, there are various levels of oxygen uptake, and that's demonstrated, that's shown by those shaded curves. So there's the oxygen uptake via the chorioallantois and the lung. And the thing you'll notice is that throughout most of the stages of the incubation, the bird is always taking up oxygen. So whether that be via the chorioallantois or the lungs, in one way or another, the bird is always taking up oxygen. So anaerobic respiration occurs in the absence of oxygen. So this question is a bit of a trick question in that it's asking us for when anaerobic respiration is likely to be the only respiratory metabolic mechanism, but the actual answer is that at none of the stages is anaerobic respiration the only respiratory metabolic mechanism, because there is always going to be oxygen available at any stage of that bird's incubation. So therefore, aerobic respiration will always occur at some level. So therefore, D is the correct answer. Question 38. Which of the following is the best estimate of the difference between the carbon dioxide partial pressures in oxygenated and venous blood? So in humans, at least, our cells consume oxygen and produce carbon dioxide as a waste product. So usually what happens is our blood, before it comes into contact with our cells, it has a very low amount of carbon dioxide. But when it arrives at the cells, offloads its oxygen onto the cells also offload carbon dioxide as the waste product back onto the blood cells. And the blood cells take that carbon dioxide away to the lungs, where it is expired from the body. And the embryo is exactly the same in this context. So a chicken egg embryo will produce carbon dioxide as a waste product and will consume oxygen. So when we are comparing the amount of the partial pressure of carbon dioxide in oxygenated and venous blood in a chicken embryo, we'd expect the oxygenated blood to have a low partial pressure of carbon dioxide and the venous blood to have a high partial pressure of carbon dioxide. So if we take a look at figure 2 for this second graph in the second box, we can see the partial pressures for CO2 in various layers of the eggshell/embryo. So over here on the left, our upwards pointing arrow, that represents the venous blood partial pressure, and if we read off from where that arrow touches the x-axis, well, we can say that the partial pressure for venous blood is about 50. The oxygenated blood, on the other hand, has a partial pressure of about 40. So the difference between the carbon dioxide partial pressures in oxygenated venous blood is going to be about 10. So therefore, the correct answer for question 38 is A. (39) Considering the system described, which one of the following is possible for the normally functioning embryo? At a point in the A bloodstream, water vapor partial pressure equals oxygen partial pressure. So if we look at our figure 2 graph, we'll notice that for the water graph, which is the rightmost box, we can see that the line for water never actually reaches the bloodstream. So the bloodstream is at this depth. We can see that the water only ever gets down through to the bottom of the eggshell pore. So it never manages to get past that outer membrane. So therefore, we can rule out A, because A states that in the bloodstream, water vapor pressure equals oxygen pressure. So A is incorrect because the water never reaches the bloodstream. At least the water vapor never reaches the bloodstream. B, at a point in the bloodstream, oxygen partial pressure equals carbon dioxide partial pressure. So let's draw up a range for the oxygen and CO2 partial pressures in the bloodstream. So this is our O2 graph on the left. We've got our bloodstream here. So oxygenated blood with this downwards arrow and venous blood on this upwards arrow. And they appear to be over a range from about, say, 55 to 20. So 20 to 55 torr as our partial pressure. That is the range of oxygen partial pressures in the bloodstream. And for carbon dioxide, we figured that out before, it's between 40 to 50. So what this sort of suggests is that yes, there is indeed an overlap in the range of the carbon dioxide and the oxygen. And since we know that in oxygenated blood, when we go from oxygenated blood to venous blood, the oxygen partial pressure is going to go down, and the carbon dioxide pressure is actually going to go up. There's probably a point somewhere in the bloodstream where the oxygen partial pressure equals the carbon dioxide partial pressure because their ranges overlap. So B is looking pretty good. Let's go through C and D. So C, at a point in the egg outside the embryo, water vapor partial pressure equals oxygen partial pressure. So if you take a look at the graph, the ranges for water and oxygen. So partial pressure range for water is between say about 45 to 15. So water 15 to 50, 15, sorry, to 45. Not super important to be super exact, but I'll just write that in. And for oxygen, the range is about 110 to 150. So as you can see, there is no overlap between the oxygen partial pressure range and the water partial pressure range. So therefore, there's probably not going to be a point in which the partial pressures are equal for the egg outside the embryo. So C is wrong, and for D, well, we're comparing oxygen partial pressure and carbon dioxide partial pressure for the egg outside the embryo. For carbon dioxide, got between about 0 and 40-ish. So carbon dioxide range is between 0 to 40 for the egg outside the embryo. And for oxygen, well, we can just copy that from before, 110 to 150. So again, no overlap between the ranges. So therefore, they're probably not going to equal at any point. So therefore, the correct answer for question 39 is B.